Relative file is a special type of heap file. It contains unordered, fixed-length records using unspanned blocks and contiguous allocation, that is, records are allocated to consecutive blocks. In such an organization, it is straightforward to access any record by its position in the file. For example, if the file has R records, numbered 0, 1, 2, etc., and R-1, BFR is the blocking factor, the number of records a block can accommodate. All the blocks are numbered 0, 1, 2, etc., and records in each block are numbered 0, 1, 2, etc., BFR-1. Then, the ith record of the file can be located in block I/BFR-U and is the I mod BFR, the record in that block. Accessing a record by its position does not help locate a record based on a search condition. However, it facilitates the construction of access paths on the file, such as indexed access, Unit 12. Records in a file can be physically ordered based on the values of one of their fields. Such a file organization is called a sorted file, and the field used is called the ordering field. If the ordering field is also a key field, then it is called the ordering key for the file. The sorted file organization has some advantages over unordered files as follows. Reading the records in order of the ordering field values becomes very efficient because no sorting is required. Remember, one of the common file operations is find ordered. Locating the next record from the current one in order of the ordering field usually requires no additional block accesses because the next record is often stored in the same block unless the current record is the last one in the block. Retrieval using a search condition based on the value of the ordering field can be efficient when the binary search technique is used. In general, the use of the ordering field is essential in obtaining the advantages. A binary search for disk files can be performed on the blocks rather than on the records. Suppose that the file has B blocks numbered 1, 2, etc. B. The records are ordered by ascending value of their ordering key. We are searching for a record whose ordering field value is K. Disk addresses of the file blocks are available in the file header. The search algorithm is described below in pseudocodes. Explanations. The binary search algorithm always begins from the middle block in the file. The middle block is loaded into a buffer. Then, the specified ordering key value, K, is compared with that of the first record and the last record in the buffer. If K is smaller than the ordering field value of the first record, then it means that the desired record must be in the first half of the file, if it is in the file at all. In this case, a new binary search starts in the upper half of the file, and blocks in the lower half can be ignored. If K is bigger than the ordering field value of the last record, then it means that the desired record must be in the second half of the file, if it is in the file at all. In this case, a new binary search starts in the lower half of the file, and blocks in the upper half can be ignored. If K is between the ordering field values of the first and last records, then it should be in the block already in the buffer. If not, it means the record is not in the file at all. Performance issues. The sorted file organization can offer very efficient retrieval performance only if the search is based on the ordering field values. For example, the search for the following SQL query is efficient. Select name, address. From student. Where ID equals 9,701,890. If ID is not in the condition, the linear search has to be used, and there will be no performance advantages. Update operations, example, insertion and deletion, are expensive for an ordered file because we must always maintain the order of records in the file. To insert a new record, we must first find its correct position among existing records in the file according to its ordering field value. Then, a space has to be made at that location to store it. This involves reorganization of the file, and for a large file, it can be very time-consuming. The reason is that, on average, half the records of the file must be moved to make the space. For record deletion, the problem is less severe if deletion markers are used and the file is reorganized periodically. One option for making insertion more efficient is to keep some unused space in each block for new records. However, once this space is used up, the original problem resurfaces. The performance of a modification operation depends on two factors. First, the search condition to locate the record, and second, the field to be modified. If the search condition involves the ordering field, the efficient binary search can be used. Otherwise, we have to conduct a linear search. A non-ordering field value can be changed, and the modified record can be rewritten back to its original location as Hamming fixed-length records. Modifying the ordering field value means that the record may change its position in the file, which requires the deletion of the old record followed by the insertion of the modified one as a new record. Reading the file records in order of the ordering field is efficient. For example, the operations corresponding to the following SQL query can be performed efficiently. Select ID, name, course. From student. Where level equals to. Order by ID. The sorted file organization is rarely used in databases unless a primary index structure is included with the file. The index structure can further improve the random access time based on the ordering field. This issue is dealt with in Unit 12. Hash file organization. The hash file organization is based on the use of hashing techniques, which can provide very efficient access to records based on certain search conditions. The search condition must be an equality condition on a single field called hash field. Example, ID equals 9,701,890, where ID is the hash field. Often, the hash field is also a key field. In this case, it is called the hash key. Hashing techniques. The principal idea behind the hashing techniques is to provide a function, h, called a hash function, which is applied to the hash field value of a record and computes the address of the disk block in which the record is stored. A search for the record within the block can be carried out in a buffer, as always. For most records, we need only one block transfer to retrieve that record. Suppose k is a hash key value. The hash function, h, will map this value to a block address in the following form. H, k, address of the block containing the record with the key value, k. If a hash function operates on numeric values, then non-numeric values of the hash field will be transformed into numeric ones before the function is applied. The following are two examples of many possible hash functions. Hash function, h, k, equals k, mod, m. This function returns the remainder of an integer hash field value, k, after division by integer, m. The result of the calculation is then used as the address of the block holding the record. A different function may involve picking some digits from the hash field value, example, the second, fourth, and sixth digits from ID, to form an integer, and then further calculations may be performed using the integer to generate a hash address. The problem with most hashing functions is that they do not guarantee that distinct values will hash to distinct addresses. The reason is that the hash field space, the number of possible values a hash field can take, is usually much larger than the address space, the number of available addresses for records. For example, the hash function, h, k, equals k, mod, 7, will hash 15 and 43 to the same address 1, as shown below. 43, mod, 7, equals 1, 15, mod, 7, equals 1. A collision occurs when the hash field value of a new record that is being inserted hashes to an address that already contains a different record. In this situation, we must insert the new record in some other position. The process of finding another position is called collision resolution. The following are commonly used techniques for collision resolution. Open addressing. If the required position is found occupied, the program will check the subsequent positions and turn until an available space is located. Chaining. For this method, some spaces are kept in the disk file as overflow locations. In addition, a pointer field is added to each record location. A collision is resolved by placing the new record in an unused overflow location and setting the pointer of the occupied hash address location to the address of that overflow location. A linked list of overflow records for each hash address needs to be maintained. Multiple hashing. If a hash function causes a collision, a second hash function is applied. If it still does not resolve the collision, we can then use open addressing or apply a third hash function, and so on. Each collision resolution method requires its own algorithms for insertion, retrieval, and deletion of records. Detailed discussions on them are beyond the scope of this unit. Interested students are advised to refer to textbooks dealing with data structures. In general, the goal of a good hash function is to distribute the records uniformly over the address space and minimize collisions while not leaving many unused locations. Also, remember that a hash function should not involve complicated computing. Otherwise, it may take a long time to produce a hash address, which will actually hinder performance. External hashing. Hashing for disk files is called external hashing. To suit the characteristics of disk storage, the hash address space is made of buckets. Each bucket consists of either one disk block or a cluster of contiguous blocks and can accommodate a certain number of records. A hash function maps a key into a relative bucket number rather than assigning an absolute block address to the bucket. A table maintained in the file header converts the relative bucket number into the corresponding disk block address. The collision problem is less severe with buckets because as many records as will fit in a bucket can hash to the same bucket without causing any problem. If the collision problem does occur when a bucket is filled to its capacity, we can use a variation of the chaining method to resolve it. In this situation, we maintain a pointer in each bucket to a linked list of overflow records for the bucket. The pointers in the linked list should be record pointers, which include both a block address and a relative record position within the block. Performance issues. Hashing provides the fastest possible access for retrieving a record based on its hash field value. However, search for a record where the hash field value is not available is as expensive as in the case of a heap file. Record deletion can be implemented by removing the record from its bucket. If the bucket has an overflow chain, we can move one of the overflow records into the bucket to replace the deleted record. If the record to be deleted is already in the overflow, we simply remove it from the linked list. To insert a new record, first, we use the hash function to find the address of the bucket the record should be in. Then, insert the record into an available location in the bucket. If the bucket is full, we will place the record in one of the locations for overflow records. The performance of a modification operation depends on two factors. First, the search condition to locate the record, and second, the field to be modified. If the search condition is an equality comparison on the hash field, we can locate the record efficiently by using the hash function. Otherwise, we must perform a linear search. A non-hash field value can be changed, and the modified record can be rewritten back to its original bucket. Modifying the hash field value means that the record may move to another bucket, which requires the deletion of the old record, followed by the insertion of the modified one as a new record. One of the most notable drawbacks of commonly used hashing techniques, as presented above, is that the amount of space allocated to a file is fixed. In other words, the number of buckets is fixed, and the hashing methods are referred to as static hashing. The following problems may occur. The number of buckets is fixed, but the size of the database may grow. If we create too many buckets, a large amount of space may be wasted. If there are too few buckets, deletions will occur more often. As the database grows over time, we have three options. Devise a hash function based on current file size. Performance degradation will occur as the file grows, because the number of buckets will appear to be too small. Devise a hash function based on the expected file size. This may mean the creation of too many buckets initially and enter some space wastage. Periodically reorganize the hash structure as file grows. It requires devising new hash functions, recomputing all addresses, and generating new bucket assignments. This can be costly and may require database to be shut down during the process. Some hashing techniques allow the hash function to be modified dynamically to accommodate the growth or shrinking of the database. These are called dynamic hash functions. Extendable hashing is one form of dynamic hashing, and it works in the following way. We choose a hash function that is uniform and random. It generates values over a relatively large range. The hash addresses in the address space, that is, the range, are represented by d-bit binary integers, typically d equals 32. As a result, we can have a maximum of 232 over 4 billion buckets. We do not create 4 billion buckets at once. Instead, we create them on demand, depending on the size of the file. According to the actual number of buckets created, we use the corresponding number of bits to represent their address. For example, if there are 4 buckets at the moment, we just need 2 bits for the addresses, that is, 00, 01, 10, and 11. At any time, the actual number of bits used, denoted as I and called global depth, is between 0 for 1 bucket and D for maximum second buckets. Value of I grows or shrinks with the database, and the I binary bits are used as an offset into a table of bucket addresses called a directory. In Figure 6.3, 3 bits are used as the offset, that is, 000, 001, 010, 110, 111. The offsets serve as indexes pointing to the buckets in which the corresponding records are held. For example, if the first 3 bits of a hash value of a record are 001, then the record is in the bucket pointed by the 001 entry. It must note that there does not have to be a distinct bucket for each of the 2 I directory locations. Several directory locations, that is, entries with the same first j, bits j, is less or equal to I, for their hash values may contain the same bucket address, that is, point to the same bucket if all the records that hash to these locations fit in a single bucket. J is called the local depth stored with each bucket. It specifies the number of bits on which the bucket contents are based. In Figure 6.3, for example, the middle 2 buckets contain records which have been hashed based on the first 2 bits of their hash values, that is, starting with 01 and 10, while the global depth is 3. The value of I can be increased or decreased by 1 at a time, thus doubling, or having the number of entries in the directory table. Doubling is needed if a bucket whose local depth, j, is equal to the global depth, I, overflows. Halving occurs if I is greater than j for all the buckets after some deletions occur. retrieval to find the bucket containing the search key value k. Compute h k. Take the first I bits of h k. Look at the corresponding table entry for this I bit string. Follow the bucket pointer in the table entry to retrieve the block. Insertion. To add a new record with the hash key value k. Follow the same procedure for retrieval, ending up in some bucket. If there is still space in that bucket, place the record in it. If the bucket is full, we must split the bucket and redistribute the records. If a bucket is split, we may need to increase the number of bits we use in the hash. To illustrate bucket splitting, refer to Figure 6.3 and suppose that a new record to be inserted causes overflow in the bucket whose hash values start with 0, 1, the third bucket in Figure 6.3. The records in that bucket will have to be redistributed among two buckets. The first contains all records whose hash values start with 0, 1, 0, and the second contains all those whose hash values start with 0, 1, 1. Now, the two directory entries for 0, 1, 0 and 0, 1, 1 point to the two new distinct buckets. Before the split, they point to the same bucket. The local depth of the two new buckets is 3, which is 1 more than the local depth of the old bucket. If a bucket that overflows and is split used to have a local depth j equal to the global depth I of the directory, then the size of the directory must now be doubled so that we can use an extra bit to distinguish the two new buckets. In Figure 6.3, for example, if the bucket for records whose hash values start with 111 overflows, the two new buckets need a directory with global depth I equals 4, because the two buckets are now labeled 1110 and 1111, and hence their local depths are both 4. The directory size is doubled, and each of the other original entries in the directory is also split into 2, both of which have the same pointer as did the original entries. Deletion may cause buckets to be merged, and the bucket address directory may have to be halved. In general, most record retrievals require 2 block accesses. One to the directory, and the other to the bucket. Extendable hashing provides performance that does not degrade as the file grows. Space overhead is minimum because no buckets need be reserved for future use. The bucket address directory only contains one pointer for each hash value of current prefix length, that is, the global depth. Potential drawbacks are that we need to have an extra layer in the structure, that is, the directory, and this adds more complexities